Hello, we are An-Dae-yoon and Yi-Ning, semiconductor majors at Dongguk University. In this project, we designed the AFSM of MP3, which automatically moves on to the next song after a certain period of time and implemented the layout. AFSM design methods include LBD, FCD, and PLD methods, among which we design and compare the same system with FCD, PLD methods, excluding LBD. First of all, the PLD method uses a switch, which has the advantage of not having to draw a K-map based on a logic table and derive a logic equation separately. It also has the advantage of being fast because it is easy to optimize the gate size or structure to minimize propagation delay. However, if you design around speed, there is a possibility of increasing area or power consumption. On the other hand, the FCD method is a completely custom structure that allows the highest optimization in terms of performance, power, and area. But it has the disadvantage of high design difficulty and error-prone. Now, let's compare the AFSM structure that we made in both ways. First, we designed the NSL for the operation of the AFSM. The inputs are A1 and A0. And at the same time, to remember the status, SM received a bundle of 3 bits and connected the signals feedback from P0 to P8 back to the NSL input. What you see on the screen is the NSL implemented by PLD method and FCD methods respectively, and it is composed of blocks D2, D1, and D0. Since NSL occupies the largest area in the entire system, we paid a lot attention to the layout adjustment to maximize the degree of integration while following the minimum distance rule of poly, M1, M2, MOS, and ACT. The data output from the NSL is transferred to the SM and stores a total of 3 bits. The system we implemented is N4, so we connected 3 SM in series. Each SM consists of 3 PTDFF.
PTDFF is Professor Song Min-kyu's patent structure, which is an edge-triggered flip-flop that captures data at the rising edge of the clock and delivers it to Q. Through simulation, it was confirmed that data was accurately captured at the clock's positive edge. This stored status information is transferred to output logic and converted into externally verifiable outputs. The screen shows the scalability of output logic and the layout based on it. The ESD and output driver are also designed for the full chip implementation. The ESD circuit is designed to protect the internal circuit from large currents. For example, when a voltage higher than 1.5 voltage is input, only the NMOS and the top is turned on to bypass the current, and when a negative voltage below 0 voltage is input, the NMOS and the bottom is turned on to discharge the current. The output driver amplifies the small current in the internal circuit to enough drive current for external use. Finally, we connected all the mentioned blocks and even configured a simple path to complete the full chip design. Based on the complemented layout, DRC and LVS verification confirmed that all passed normally without any design rule violations or schematic layout mismatch. Eventually, the AFSM we designed was found to be more efficient in the PLD method. According to the advantages and disadvantages of PLD and FCD that we summarized earlier, the PLD method was designed with the least number of gates, so there was definitely less delay. And FCD is a design that customizes everything, so we confirmed that it was efficient in terms of area. So far, I've explained the AFSM design process and results implemented in FCD and PLD method. I'll finish the presentation. Thank you.